Hi Fahima. Hello.
Good evening, sir.
Yeah, good evening Fahima. We'll start the class maybe after 2-3 minutes. We'll wait for if anyone joins.
Okay, sir.
Okay, thank you. I think we'll start the class. One second. Fahima, you can see the screen, right?
Yes, sir.
Okay, fine. So, just give me 1 minute. Yeah. So this will be the hi all. This will be the last class of this assignment section for the. This is week 12's class, and in the, I mean last Saturday I have taken one class where I have discussed a few part of this today's class, and I mean if you can recall it, and I example the water example. Uh, I mean that video is also uploaded with the name week 12. You can see that video, and in that video I have shown how the Gromax software works, which is the suitable one for the to do the MD simulations. I mean there are other softwares also, like there is a LAMS for small molecules, but mostly and if you want to add the molecule, if you have seen the video, okay, I mean there are different software. There is a, like a named there is a named software, and there is a pack mole to add the molecules, and there is how to say it, and there is if you and there is pymol for to study the protein analysis, which is nothing. Then there is this is all nothing. So but for thermodynamics point of view, the Gromax, the lamps, and NAM, and the packmol, these four you can use to add the molecules to get into the system. So as of now we studied the classical and the statistical. So in classical we discuss what are the different types of laws we have, and then we have discussed the entropy from the work thermodynamics second law. We discussed the entropy, how the disorderness increases As the temperature increases, the disorderness increases, as because you can remember this example as if you have a liquid of water, solid, this is in ice form, this is at very low temperatures. As if somebody asks you what will be the entropy, if I increase the temperature, if I increase the temperature, take the example of this, the ice molecule will be very packed, and if you increase the temperature, the disorderness will be increased. Okay, you can remember like this. And then we studied the different laws, and then we studied for the real gas situations and ideal gas situations, how the different parameters changes and all the things. And then we come to the statistical, we started with the thermodynamic probability, and then we found out that here we have the distinguishable elements. Sorry, initially we made the formula with the distinguishable elements, then we carried out to the indistinguishable elements, where we got the degeneracy, indistinguishable. So if you go through the distinguishable and indistinguishable, we have the different number of microstates, different number of microstates, where we got the, due to this different number of microstates in the distinguishable element, if you see the, how to say it, the entropy term, which need to increase by increasing the terms. So the, as volume increases to Vn and the number of molecules into 2n, the entropy is not increased to 2s. So then we come to the indistinguishable elements, where we got, so we assume that okay, the thermodynamic probability with indistinguishable particles can explore the, how to call it, thermodynamic probability. So then we started the ensemble approach. From ergodic hypothesis, where he says that ensemble average will be equals to time average. And in the length, I mean in the week 11th class, in the video also you can see what do you mean by ensemble and what do you mean by macrostate and microstate. So M1, M2, M3 macrostates. So will always be equal in macrostate but differ in microstate. So if you run for the long interval, you will get the probability density higher. So sorry, probability density higher. So it means you will get the proper values of the experimental values, proper experimental values. And we have seen the formulas for this, the ensemble average and Q, if you go to the previous classes. And then we come to the force field. Before saying the force field, I will come to the term the pair potential. So when you have taken the box and we kept the molecules inside the box, we discussed that okay, there will be surface effect, then there will be pair potential between these two atoms, then these two atoms, and then there is an atom between these three. So we gone through the pair potentials. So initially the potential energy is defined with the aspect of surface effect plus pair potentials, and we are not considering more than two pair potentials because it won't have much effect on the system. So then we have different types of like a hard sphere, a square well, and I think the next name is soft sphere. Yeah, hard sphere, soft sphere, and the square well. Potential, we have seen these three potential how they are calculated, and in these three sphere potentials, so they are calculated either attraction or repulsion, but they didn't carry out the both. So when we have the in the motion of the systems, we can't rely on either one of these if you are going for the biomolecular systems which are very big in the size. So then comes the LJ potential. So the formula of LJ potential is sigma by r 2 to the power r sigma by r to the power 6, and which gives here the minus term gives for the attraction, and this is for the repulsion. And you are seeing this diagram, the diagram will go like this. So up to here there won't be any interaction. This will be the epsilon and this will be the sigma. I mean the how much interaction we have, and we have gone through and there will be a, if you want, this is for the short range. I mean when the molecules are too near, then only we can calculate the LJ potential, and if you want to calculate the long range, then we will go for the ionic interactions. If I am talking about the ionic, then we have the Coulomb potential. So the Coulomb potential formula is so this is the Coulomb potential for the long range. So then whenever I am speaking about the system, these are the pair potentials, how we can calculate the pair potential. So now we have, this is for the intermolecules, is intermolecules. I mean we have one big system here and there is another big system, and if you want to calculate the between these two atoms or these two atoms or these two atoms or any other two different atoms of two different systems, then we have the pair potential. Or what about the systems within intra system, intermolecule? So then we have for intramolecules we have bonds, angles, dihedrals. So now the UR will be U of R plus inter plus intra. So now the inter means whether you will, sorry, this U of R will be there, plus inter means the short range when the molecules are too closely near to each other and when the molecules are far away. And then we have the bonds, we have the dihedrals, we have the angles. And to remove the surface effect, suppose if you have these molecules and the, I mean the energy should be same, right? As the systems energy should be same, but if you consider there are these molecules, the energy of this molecule will not be same to the energy of this molecule because it has a surface effect, where this molecule will not have the surface effect, it has only short range long range interactions. So to avoid this extra energy particles, extra energy term, so we have gone to the periodic boundary condition, where we have created the different, again one of the periodics on all three directions. It depends like whether you want to create on all the three directions or any two directions or any one direction. It depends upon the formula. um, how to say it, say suppose if you want to create it for the, I'm just saying it, I will explain you that part also. So in this part, in this way you have done the PBC condition, and then from the PBC what you have done was, say suppose if this molecule is going this side, there will be some molecule which is coming inside. So in this way you have nullified the surface effect, you remove the surface effect. But the problem with the PBC was you are calculating all the systems, so it means n square atoms. So it means you are calculating this atom, this atom, this atom. So there are, if you are n atoms and n size, so you are doing for the calculation of n square atoms. Then comes the minimum image convention. So once the PBC is done, we get the minimum image convention. So where what we have done was we have taken a particular molecule. If you want to calculate of this, then we made this as a center and we made the box around it, and what are the atoms inside it. So then we calculated and we got n into n minus 1 by 2. So to reduce this further, we have developed the cutoff scheme, where we have said that okay, this molecule can go up to this range, up to here, which can have interactions up to here, only this, and beyond this don't consider it. So then further we reduce this to some more elements. Okay, this is what we discussed in the week 11, and after that I have showed, suppose the PBC condition. I will show you one example. Yeah, if you remember this example, just assume this example, and I will draw the same again. So there are three cases of seeing the diagram. So suppose the first case is, so this is the box and you kept the bilayer in the center. Okay, so assume this is the bilayer and this is filled with water molecules. Okay, so now suppose if the box size is very small, and if you do the PVC of this one, it will go like this, and the top also it will come like this if you do the PVC of this condition. and the distance between these two will be very small. See, suppose here if I draw this, so here the distance will be so small that so you should not do it on the 3 axis, so you can do only on the xy direction. Suppose if this is the box of and you are adding the lipid bilayer in the middle, so you should not do the PVC on this side and this side if the box size is very small. But if the box size is so big, then you can do it. I mean, if the box size is so big, then you have the, because we are pulling the drug from here, right? Say suppose you are pulling the drug from here to here inside, so it will have the ample of time. If suppose if you are pulling the drug in the small box, it will have the PVC condition, then it will jump to the another box. So the overall the result will be very less. So that's why when you are taking the small box, then you need to extend it. But if you are taking the large enough box where the molecule can go like this, then it's fine. You got my point? What I'm saying, the PVC condition. So you understand, right, the PVC condition effect. So here you can only apply the PVC on XY direction, not on the Z direction. But if you have a large box, then there is no issue of PVC, then you can do for XYZ. So you need to understand how the PVC works. If you have a doubt regarding this, you can ask. Okay, fine. So I will move forward. Then we have seen the example of the Gromax, the tutorial. So have you anyone used the during the call? Okay, have you anyone used the Gromax? I'm audible, right? Hello.
Yes.
Yeah. So have anyone of you used the Gromax software to do any simulation, MD simulation?
No.
Okay, fine. Okay, fine. So this is one software. I mean, if you have seen anyone doing from the biotechnology, if they are doing the simulation, they will use mostly this software, the Gromax one. Uh, so yeah, can think of it. So yeah. So in this, we will give the. I have shown you in the last class. In the Saturday class, I have made the water molecule system. If you have seen that video, you'll understand that how we can add the system details and all, which you can see it later also, that video. So now, if I'm talking about the MD simulation, we know that the main two important parameters are the coordinates and the momentum. So if you see, the whole formula depends upon this. So now, as I said that if I run long enough, the ensemble average will be equal to time average. So I know R0 and how to get the say suppose 1 second time after 2 seconds. No, it will go in the microsecond, picosecond, femtosecond scale, but still remember like this. So how to get this data in the time scale? So to get the data, what I said was, if you remember, the microstate is nothing but the so if you see here, the difference is Ri. So initially it will be at some position, it is changing these things. As you see, the macrostate will be same, the microstate is different. So you need to remember that we need to understand that how we can go from R0 to RT. So for this, we need to understand the small things. Before this, we have one segment called as force field parameters. So in force field parameters, from the name itself, we understood that it is a force field and it is a parameter file. So basically, in the Gromax software, or in the not only in the Gromax, so if you want to calculate any difference between the two atoms, we need to have some libraries. Otherwise, how can the computer knows that okay, that bond between the initial values? Say suppose, as I said, we have the initial coordinates. We need to have the initial parameters also, right? It's like if you're doing any experiment, you need to have the value, right? The what you call the blank values, the initial values. In the same way, it is also initial values. from initial parameter we need to feed to the system, so that will be given in the form of force field parameters. Okay, what does this force field parameter consist of? It consists of the information between the sigma values, the epsilon values, the bond values, the angles, and the dihedral values. So it consists of all those values, the initial values. Okay, if I given that, if I have the atoms like this, I'll remove it. So what I will do was I'll add the double bond here. So 3, the 4, 3, the 4. So now in my parameter file we'll give the numbering. So suppose if I give the numbering 1, 2, 3, 4, 5, 6, 7. So now if I am writing about the bonds, I will make it in the new slide. So if I name it 1, 2, 3, 4, 5, 6, 7, double bond 1, 2, 3. So we need to have one more hydrogen. 8, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Okay. So now we have 8 atoms. So the force field parameter will store the values of C, C bond value, the C double bond C bond value. It will not store in the C, C value. It will store in the form of the numbers, because we already once defined here, right? So we already defined here. So now it will take the like this. Suppose if I am talking about 2, 3. So it will be 2, 3. So 2, 3, and then it will. So here we will have the formula, right? If you remember. So it will take the initial value, and we have the KL values also here. So we have R0 initial value and KL values. The KL is constant, so it won't change. 2, 3, what is the R0 value and KL value, and this is the initial value. It will take as R0. Then at R1 position, what is the value? Okay, so that's what we will get it. So then the system will have 1, 2 values. 1, 2 is nothing but C double bond C. Then it will have the 3, 4 systems, and then it have the 3, 5 information. You need to remember that it has the information of 1, 8, 1, 7. You can write it in one form. You don't need to write again 3, 2. Okay, you can write, if you write 2, 3, it will take the 3, 2 also. The same thing for angles and all the things. So you understand what the force field parameter does. And in the force field parameter, we have the different softwares: Amber, OPLS, there is a charm. So what is the use of this was, so suppose there are 3 people who have done the 3 different experiments, and we need to understand that from the literature, you need to focus more on the literature if you are doing some experiments. There you will understand that, okay, why, suppose if somebody asks that, okay, you have, in one of the papers they asked for us that, okay, why you use the amber, why you used the amber force field parameters? Because say suppose in amber, I want to connect it between two bonds, it has a value of 1.3. The same value in the charm, it will be 1.313. In OPLS, it will be the value of 1.292. You may feel that this value will be very small in small scale, but if you coordinate this for the 8 atoms, I mean, I'm given the values of 1. If you coordinate this for the 8 atoms and the 8 bonds, 8 angles, 8 dihedrals, and all the so on, the value will change in a huge scale. Okay, so they ask that why use amber, not any OPLS or charm. Then we have said that, okay, from the literature we have found out that amber is the most suitable one, and they even sometimes they will ask that, okay, can you prove it, the authenticity of the amber force field? So then we need to take any new system, and then we need to do the simulation to figure out that which one will give the better result, either amber or OPLS or charm. Okay, it depends upon your literature, okay, which molecule to be taken. So once we have done with the force field parameters, then we have the algorithms. The sir in the class has explained very well, so I will go through the, like, in the same thing in the different format. Why we need to have the algorithm was, say you have R0 system, x comma y comma z, at initial stage, and you need to get at RT, and you need to go on so on at stage 1, stage T, and so on. So how to get these stages? So we know that function is nothing but the force acting on the system is nothing but the potential energy, derivation of potential energy, and the MD simulation runs on Newton's second law of motion, where F equals to mi into ai. You need to remember this. This is the basic equation of MD simulation. It's like the force generated when a object of mass m moves with the acceleration a. So that's how it has generated things. Yeah. So you need to remember this. So now we know that force is nothing but du by dr. It is equal to mi into d square r by dt square. So this one, if I write it, f equal to miai. So f is nothing but du by dr, nothing but mi into dv by dt. This is velocity. So now m into d by dt of dr by dt. So velocity is nothing but distance by time. So now we have this formula. Yeah. So now you need to get, if you solve this, what you will get was, so you know that at each stage you know the potential force, and if you do this you will get r of t. So that's what we need to have it, r of t. So how to do it? So to get the new coordinates, we will split this equation, the second order equation, to the first order equation. We will convert the second order equation to first order equation for simplicity of the calculation. So now what we'll do is, so now we know that a equal to dv by dt. So this is the first equation which we have done from here. So now if I write dv, so if I apply integration of 0 to t, a dt equals to v naught to vt dv. So now if I wrote v equals to vt equals to v naught plus at. So assume this is the equation 1. And the second equation is v equals to dr by dt, and dr equals to v into dt. Yeah. If I apply the integration from r0 to rt, so we get rt minus r naught. So we know what is the v naught here. V is nothing but, we will apply here this one. So v naught plus at of dt from 0 to t. So now rt equals to rt naught plus vt naught t plus of at square. So any doubts in this equation? So then we know that f equal to miai. So remember these three equations. So the first equation, the second equation, and the third equation. We need to connect these three equations. So now we have the basic equations. Say suppose, okay, if I have the initial coordinates and if I have the initial velocity, so the unknown terms are, the known terms here are, only RT is the known. Okay. So we don't know what is the acceleration. Because RT you will get directly, say suppose you draw some molecule, say suppose you have drawn this molecule, water molecule. So in any software you will get the coordinates, right? X comma y comma z of this system. Okay, this is what you will have initially. So you don't have v naught, you don't have a naught, a. Okay, if you have any one of these things, then you can understand it. So now we need to understand that, okay, how to get the v naught. So for that we have the Maxwell-Boltzmann constant relation. So initially we have applied some random value to the velocity. So here also in the same way we will get the max from Maxwell-Boltzmann velocity. So by using the formula from Vmax to V minus x minus Vmax. So we have initial coordinates. So we will get the V0 also initial velocities randomly, which will be generated from the Maxwell-Boltzmann distribution by using the two assumptions. So one is momentum will be always 0, and the second one kinetic energy will be equals to 3 by 2 nkt. If you remember, we got this formula from the thermodynamic probability. While deriving the thermodynamic probability, we got total energy. So here we got the kinetic energy as total energy. So by assumption of these two, we get this one. Now how to get RT? Say suppose, so now there are different scientists who have developed some algorithms to find out the R of t plus delta t. So very few one of them are Verlet algorithm, leapfrog algorithm, velocity Verlet, and another one is yeah, you can remember these three are the important ones. So you can see the Verlet. Now we can compare the Verlet and leapfrog for, as sir said in the class. So in the Verlet, so basically we have these two equations, V of t equal to V0 plus AT and RT equals to R0 plus V of t into of AT square. So now if I want to get RT of delta t, it should be RT is constant, so it will be V of delta t, because t plus of t plus delta t equal to at new combination it will be delta t. So you need to have this one. Then we have of delta t square and the A of t and the fir. Okay, so now if you go for a Verlet algorithm, so we will go for the first initially Verlet algorithm. So here the formula is R of t plus delta t equals to RT plus V0 dt plus of AT plus of dt square of A of t. So this will be same. So now it is minus dt, right? So it will be minus dt. So minus of square will be there, right? So it will be plus dt square of ATT. So now what I will do is I will add the both. So now you will get R of t plus t delta t plus R of t minus t delta t equals to 2R0. This will get cancelled. So then you will get dt square A of t. So half of 1, right? So 1, yeah. So now you will get so if you want to know R at new position, say suppose if you want to find out R at 5th second, is nothing but 2 R at initial minus R at 4 plus dt square A of t. So from here you can understand that you will get the 5th second coordinates using the initial and the previous one. But here the basic drawback of Verlet is it won't calculate the velocities. Okay, so to further to correlate the velocities, the leapfrog was what he done was he has done the calculation with respect to the velocities also. So we know this formula. So then we know this formula also. So if I write it here, V of t equal to V0 plus AT. So that's what I'm writing here. So it will be v naught plus, so half dt, right? So you understand, right? So it will be, so it will be like a will be common, so it will be t of half dt minus t, so this will get, so we will get half dt. So you understand, right, how we got the half dt, or otherwise here how got dt square and all the things. So in this way, so we are taking the first step, and we are taking we are taking the final step minus initial step. If you do this calculation, t plus half dt minus t, you will get a cancel and you will get half dt. So yeah, what he has done was, so from here, from say assume this is the first equation and a and b, from here what we got was, so if we are taking common, v of t plus of dt a of t, which is nothing but this one. So now, so what does this formula says was, if you know velocity at before, so suppose if you want to find out the r5, say suppose r1, you need to have the coordinates of r0 plus you need to have the coordinates of v 0.5. So now to get v 0.5, how to we'll get the 0.5? This is another question. So for this we will do the same way how we did this for this way. So v of t plus of dt equals to v of t dt a of t we will do the minus, so it will be v of, so because we don't know the tmt, right, because we want to find out the t plus delta t, and then we will get, so it is minus, right, so it will be plus. So it means if you want to know the v 0.5 seconds, here we need to find out the v 0.5 second. So if you want to find out the v 0.2 second, we need to get the v 0th plus changing the time of at. So it's like v 0.5 equals to v 0 plus dt of a1. So the dt will be 1 here. You understand, right? So suppose if you want to get the from the leapfrog, it's like simple. So if you want to find out the r1, you need to have the command of v 0.5. To find out the v 0.5, we need to have this. So in this way we are getting the dr with, so we are considering the dr and velocities both together here in the leapfrog. That's why the leapfrog is the most suitable one for the simulations. So basically what it says was, so if we have r0, r1, r2, r3, so we are calculating like this, we are calculating r0, r1, r2, r3 and r4, but the velocities are calculating like, see, if you calculating v 0.5, and then if you want to calculate the r2, so r2 will be like you are going for the r1.5, so it will go like this. Okay, so that's why it's a leaping, right? So it's like one another one, so that's why it is called as leapfrog. So this is one of the most suitable one, because we are using here the both velocities and the coordinates. So in this way you will get the coordinates. So from the first coordinate to second coordinate. So if you have the random values, so suppose initially we have assigned the random, we have r naught from the x comma y comma z from the diagram, and we will assign some random values from Maxwell Boltzmann. So then we will get the coordinates over the time. Okay, but now the question is, if you see the formula of, say suppose Verlet only, if I am talking about the Verlet, so it is basically I think 1.5 if I'm not wrong. R1 is equal to 1 plus 0, dt is 1, it's like R0 plus dt, yeah. So now if you see this one, here we have the acceleration term, even in the Verlet also we have the acceleration term. So how to get the acceleration? So because see, if you given the random velocities initially and we have the coordinates, we can get the formula, but in the formula the unknown is the acceleration. So you understand, right, what we are discussing? So we are discussing how to get the new microstates over the time. So any doubts in the how these two are happen? How we can get the new microstates? If you're not understanding, I will explain it again. I mean, the conceptual wise.
You can explain it with another example.
Sorry, I can't hear you. Your voice is breaking.
You can, no, so can I explain it with another example?
Okay, another example. Okay, fine. Say you have the system. Say you have the system of water molecules. I'm just giving the example. If I'm talking about the ensemble, you know, say suppose this is the big ensemble. We have n number of microstates. We have up to n. We have n macrostates, where 1 equals to 2 equals and so on, and we have different microstates. So microstate of 1 m1, so assume that this is micro m1 is not equal to m2. Why? Because the coordinates initial will be changing. So now we are considering how these coordinates are changing. Okay, how these coordinates are changing. Okay, so how can we get it? Through the mathematical equation. So that's what which we are studying. So how the system will do the analysis of to get the different different microstates. So that we know that the basic equations are the force applied by the body is nothing but the object with what velocity it is moving. So from here we are derivating all the formulas. So we know that the potential force is nothing but the energy acting on the body is nothing but MIAI. So remember this equation. So this will go to d square by dt square. Here we have the second order equation. So mathematically doing the second order equation will be tough. So that's why we are converting this two into this second order into the first order equation. So if I convert this, so we have two first order equations. So A equals to dv by dt and V equals to dr by dt. So it will go like dv equals to A dt, dr equals to V dt. So it will be like Vt minus V naught equals to A dt, At. So Vt equals to V naught plus At. So I will put this here. So it will be Rt minus R naught equals to V naught plus At dt, integration of 0 to t. So now it will be Rt equal to R naught plus. So these are the two basic equations. Okay, and now so the two basic equations are, so this is the first equation. Sorry, V not T. So these are the two important equations. So now say suppose you are going from 0 to 1th position and then 2, then 3, then 4 seconds. So you are going from 0 to 1 to 3. So it's like here it's like T1, T2, T3, T4, T5. So now the delta T is 1 here. So now say suppose it's like initially if delta T is 0, I mean if I start from T1, so now I have the RT1 command, then I need to get it to RT2, then RT3, then RT1, T2, T3, T4, then RT5, which says that RT1 plus 0, RT1 plus 1, RT2 plus 1, RT3 plus 1, RT4 plus 1. So it's nothing but R of T plus delta T. I mean it is going in the long scale. So now we need to we have these components. So initially we have, right, R of T1 is nothing but R at 0th position, which if you use any softwares like Avogadro, say forget about Avogadro also, if you take any image of yours and assume that you are running simulation on that, and if you get that image and if you put it in the any softwares, you will get the XYZ coordinates of that image. Say suppose if this is the image, assume this is 0, 0, 0, it is 1, 0, 0, this will be 0, 1, 0, and it will be third axis will be 0, 0, 1. So for every small particles of your image, you will get the XYZ coordinates. So that is initial coordinates, and we need to go, how can we go from the initial to the subsequent? The same with the velocities also. So how can we go from V1 to V2, V3, V4? So for this we know the formula for R naught. So what does it says was the V naught here and the A changes with respect to the time, because that's what, right, the T, if T changes, it's not the R naught is constant, not the V naught and the A, because it both will change with respect to the T. So now if I'm writing it as, so we can write it as a function of T plus so now if I want to get the T of T delta T, so now it means I'm getting the new position from the old position. So this will be there. So this will be V of T into T plus T delta T minus T plus off into A of T dt plus dt square. I think, yeah. So now this is the equation. So now just remember this equation. This is for R of T. So now what we are doing was, the leapfrog what he has done was, Verlet. In Verlet, to get the equation, he has taken the different term. So he has taken, suppose what he has taken was, so assume that you are here, okay, you need to go to here. So this is T plus delta T. So to get this, what he has done was, he has calculated this one also, T minus delta T. So that's what T minus delta T. So that is nothing but so for going forward, he has taken the values of the backward, and then what he has done was, so we don't know, as of now we don't know the velocity, so he cancelled it. So to get cancelled out, he has done the addition. So this two will get cancelled, so then it will come as, so this is the formula for Verlet, the Verlet scheme. So in Verlet, what he has done was, he has just taken the coordinates. Okay, he has taken that initial coordinate. Okay, we know that how to go forward. So for forward, he has taken the backward answer. With the help of backward, he has done it. So here if you see, T dt, sorry, this will be like minus, yes, minus So here to go forward, so this is like a forward. To go forward, he has taken the coordinates of the backward, and then he subtracted from the initial, and then he added the acceleration term. So here if you take, he has r comma r and the acceleration, but here he missed out the velocities. So to add the velocity terms, the leapfrog has come forward. Okay, he has done some mistake considering that, okay, leapfrog, what he has done was, so initially uh, we know that, right? We said that initial v naught we can get through Maxwell Boltzmann constants. So like randomly we are applying some velocity to the system. So then what he has done was, so he has taken the same thing to go forward, I mean to get the new equation. The formula is p of t plus of at square, and then what he has done was, he has taken the velocity at very low step, so he didn't go for very big steps. So we know the formula of v of t equals to v naught plus a of t. So I mean if this is 0 1 2 3, so if you are at here at 2, you need to go to the 3. So what he has taken was, he has taken the velocities at 2.5. Okay, so he wants to calculate the velocity at 2.5. So what he has done was, so he has taken the v naught. The v naught is constant. Okay, if you remember, this v naught is constant, not this one. Okay, so now we have a of t of dt. So now what he has done was, so now he has taken this formula. So you understand this concept, right? So this v naught is constant, not this one. Okay, because this is changes with the time. Because if you see this equation here, if we got v naught dt, okay, so this will get changes with the time. Okay, you need to understand it. So equals to r of t plus dt common. If you take dt as common, so then it will be v naught plus of a of t dt. So here we got so from this formula what we get was, to get the value of 3, r at 3, you need to have, sorry, this will be r0, right? This is the initial value, r0. Sorry, I made the mistake. So you understand the concept, right? So basically this is r0. So you need to have the coordinates of 0, r0, this one, and then plus you need to have the coordinates of 2.5. So how to get the 2.5 coordinates, sir? So v 2.5, what he has done was same like Verlet. So what Verlet has done for the momentum was, he has gone one step to get the one step forward. He has taken the coordinates of one step backward. The same thing leapfrog done. So what he has done was, he has gone one step backward. So he has taken the 1.5. So no, it's not off dt. I think, yeah, t of dt equals to, so from here what we get was, if you do minus, this will get cancelled. So to get the v 2.5 equals to a of 2, I mean a2, dt is nothing but 1 plus v of 1.5. So if we know the value of 1.5, we know the value of 2.5. Understand the concept, this one? So here in this term we have the velocity. Where is this? Yeah. Here for the radius, for the coordinates, we got the coordinates and the velocity, and for the velocity you use the acceleration. So here we have all the three components, which will give rise to this coordinate, second order equations. So the leapfrog is called because, so it goes, the coordinates calculation will go in the form of this, but the velocity coordinates will go in the form of, say suppose if you want to calculate the 2.5, oh sorry, for the radius 3, r3, if you want to get the r3, this is the r3, you need to go for the 2.5. For the 2.5 you need to go for the 1.5. So that's why it is one is leaping on another, so that's why it is called as leapfrog algorithm. So which is the most suitable form. So if you have any doubts, I will explain it again.
Yes, sir.
So now if you remember that as of now we are talking that we have the one second. Yeah. So we have the r9, r of t, how can we go from 0 to 1, or the velocity how to go from 0.5 to 1.5. Okay, so we have explained this concept, so but acceleration term we are forgetting. So because without acceleration we are not doing anything, right? So if you see here, to get this value we need to have the acceleration at a of t, 2 point. So suppose if you want to go for r of r1, r1 is nothing but r0 plus v.5. So v.5 is nothing but a1 plus v0, sorry, r, this will be the values which we are adding, so this will won't get. So now we have the v0.5. So now if you want to go for r2, so it will be like r0 plus v1.5. so v1.5 will gives as a1 plus v.5. so I will write it here. So r2 you will get it from r0 v1.5. so for to get the v1.5 we need to go to the a1 plus v.5. okay, so now we know this value. So how to get the a1? So you know that acceleration is nothing but, so you remember this formula, right? So initially, so you know the bonds formula and everything. So if you remember in the last class, sir has teach the potential electrostatic. I will go through the electrostatic. So you know the formula of electrostatic. So now if I apply d by dr, so it will be like z1 zj. So now if I do, there is again a. If I do it on this, so now we have du by dr. So but acceleration we need to get it on the 3 directions, because we need to go this way or that way. So now we have x comma y comma z directions, 3 directions. So you need to apply on the 3 directions to get the du. So what you will do is equals to du by dx into du by dr. So we need to, sorry, one second, I need to add more slides. So yeah, to get the acceleration on the 3 directions we need to do du by dx, so which is nothing but du by dr into dr by dx. So if you do this as sir said in the class, so it will be z1 zj by 4 pi epsilon naught rij square into x by r for the x direction, because r is nothing but the distance between the two particles. So it is nothing but x square plus y square plus z square. So if you do this you will get x by r. Yeah, so this is on for the electrostatic, and you need to do the same thing for the long range and all the du terms, and then if you add it you will get the acceleration term. So this is how you will get the new coordinates for the system. Like if you run for the long enough you will understand this terms. So that's why the potential energy is important here, because from the potential energy you will get the acceleration, from the acceleration you will get the velocity, from the velocity you will get the new coordinates. So any doubts in this? So with this we completed the MD simulation, and so once you have run the system, say suppose, yeah, I think MD simulation is done. Then we will go for, say suppose if you have run any analysis, suppose as I showed in the example, you have the protein here and you have the drug here, okay. And say suppose you want to see that how much time the drug is binding there. So what you will do was, and how does it affect? Say suppose somebody has any illness, and you know the what is the protein causing that illness, and you know that say in the market there is one approved drug for that particular illness. So now you want to see, okay, whether you, now your objective is to increase the unit efficacy by developing a new drug. So how can do was, so you will take the protein initially, this is the protein, and you will apply the drug, and you will run the MD simulation to understand that what are the effects of the protein on the drug on the protein. So what it will do was, so after some time you will see that, okay, you run for say suppose 100 nanosecond, okay, and now you need to understand analysis. So you can do the different types of analysis for this system. So the basic tools are RMSD of protein. Okay, so now you have run the long enough, and now you have the protein like this initially. Say suppose the protein is like this, and maybe in RMSD analysis, say suppose initially you have the protein like this, then it might be gone like this, it might be gone like this, it might be gone like this. So there are different types of microstates. So this is first microstate, M1, not micro, small. Yeah. So you have at time t, you have nt microstates, nt. So now you will calculate the RMSD. You will have the initial one. So initial is nothing but M1. So what you will do was, so you will calculate the RMSD. RMSD is nothing but the deviation of the backbone atom. So you will take all these atoms, and you will note down the RMSD differences, and then you will say that, okay, whether the system, say suppose without any drug, if the system goes like this, and with the drug, if the system goes like this, it means initially the system has done some increasing configuration changes. So suppose here, if you see that there is a, this is time, this is RMSD, and if you see it here, so over 50 nanosecond, assume it, so there is a exponential increase. It means initially the structure, if you see that the fluctuations are more compared to the final stages, so it means the approved drug has shown some effect compared to the no protein, compared to the no drug. So this type of analysis you can do. Then you can analyze the RMSF, the fluctuations in the particular amino acids also you can calculate. And then you can calculate the how the drug is binding to it, so to the binding energy. And there are different types of analysis based upon the system you can find out. So this is the analysis system. So we are done with the MD simulation, where we have used the Newton's equation of motion. And then further we have used the second order equation to first order equation. And we have carried out the things, ensemble average. So it means we are going from R0 to R1 to R2 to R3 to R4 and so on. Like we are going step by step. So these are the things which is happening in MD simulation. And there is another type of protocol for to run the simulations, that is Monte Carlo simulation. So basically Monte Carlo drives on the probability method. So whatever the Monte Carlo method which we are discussing sir in the class was Metropolis algorithm method. Metropolis. So now what this method was, it has 4 steps. The step 1, step 2, step 4. So now what does this matter? So see, if you see in the MD simulation also, what we are doing was, we are generating the new microstates. Okay, that's what, right? So basically whatever the simulation we are doing, we are generating the microstate. So suppose we are going from this microstate to this microstate, and then this microstate, and then this microstate, and so on to this. So basically we are generating the new microstates, which means new conformations. So the same new the how does Metropolis design the new conformations is because of the random number. So as you said in the GROMAX, so basically I work with the GROMAX. I have little knowledge about the Monte Carlo, but from the class I understood what you can understood was there is a random function which assigns some value to the new coordinate to design the new coordinate. So it goes from 0 to 1. So in the first step we will assign a new coordinates. So we will go by step by step. So we will get the new coordinates. So suppose you have drawn some structure and you got x comma y comma z. So now you will get x new using the x fold plus 2 times of zeta factor minus 1 of displacement change in the R max. So now the zeta max is nothing but the random function which assign a random value. So suppose it might be 0.1 or it might be 0.3. It assigns randomly, and if it assigns randomly, you will get the new coordinates. On the step 2, we will find out the energy of this new coordinates, new system. Okay, we will find out the energy of this new system. And in step 3, what we will see was whether if we will apply like if clause, whether we will see that if E new is less than E old or not. If it is less than E, if this is the condition, then we will accept it. If this is not the condition, then we will go to the step 4. And we will see the probability now here. So now we will see the probability of old by old. Whether this and this formula is exponential of minus E old divided by kbt. So now what we'll do was, so this is the probability of the new divided by old one. So this is the main step which we can say. See, up to here it is like a random. It's like, okay, we have given the random generator and with the generator. So suppose if the values are, if this is not the case, then what we'll get was, we'll take the probability exponential of this one. And then if you see that, if the random number which we are given, if it is less than or equal to e to the power minus of, then it will be acceptable. So you understand, right? So this value should be less than this value should be less than this, then only it is acceptable, otherwise it's not. So in this way the Monte Carlo generates a new conformation. So from one conformation to another conformation, and at the end ensemble average we will do and we will get the values of this. So any doubts in Monte Carlo?
Yes.
So yeah, if Monte Carlo is done, and I have seen assignment questions for the last week assignment question, mostly it's like theoretical only. I mean, if you see this video or like the SARS video, you'll understand it directly. And there are some few problems. So for the problems, what you need to understand was, you need to understand the classical, you need to mix the classical with statistical. Okay, you need to understand these two. I mean, for the sums, so we know that they are given some properties for the W, and say suppose you know the W, and they say that the energy is up. They given the Q values. They say the 2% is converted, right? So from there you can get. You need to understand the relation between from the classical. If you revise the notes, you will get the relation between change in entropy with respect to heat and with respect to Q comma T. So I don't want to mention the equations here. So you need to go through this equation, and then you know this is recently we seen, and then ds equals to k into ln of 1 minus, I mean the ln of final minus initial ln of initial. So they are asking this value, you know this values, they given this value, they given the t value, you keep this relation between ds equals to, there is an equation here. If you put that equation, say suppose this is x by y equation, so x by y equals to, sorry, k into ln of w1 w final by w initial, you know the kb value, they given the kb value, then this will be like x by y divided by kb exponential. Okay, you can do this way, that sum in this way. Okay, you need to understand that, okay, what is the, how does the entropy, see, because in the statistical thermodynamics the only way which we said that was initially, this is the formula, right? So from this formula you can get s equal to k ln w, and then we know from classical how does the delta S, changes in the s relates with the q and t, and if s is changing, the w will also change from one point to another point. So from one point to another point, then you need to understand this formula. So if you remember this, you can solve this. And the second question was, there is a given the partition function and the probability function. So it is nothing but, if you remember, 1 second, I'm just writing a formula. So if you remember, while you are solving the initial classical Stirling approximation of, if you remember this formulas, ln w factorial, and then we come to this formula. We have come to this formula, right? While solving this formula for alpha comma beta, we have come through one equation. If you remember it, it will goes like this: e to the power minus I by kbt divided by partition function. So this partition function q will be sigma of e power minus e by kbt. So you remember these equations? I mean, you can go through your notes also, you will get this equation. And if you have these equations, you can solve the class problems. And if you have any doubts, or 1 second, so still you have time. If you have any doubts, you can ask me regarding the class or anything. So in the last week I shared the GROMAX tutorial also. You may find out that tutorial again. If you have doubts, you can ask me. If you have any queries also regarding thermodynamics, you can ask me that, okay, what are the queries you have on this stuff.
Sir, for those reference sheets,
Yeah,
steam table and all, will they provide?
sorry?
No, sir, for steam table and other reference sheet, will they provide an examination?
I think I too don't have idea. I'll let you know, okay? I'll ask the coordinator and I'll let you know, okay? I think they will provide it, okay? Otherwise they will give the values. If the questions will come, they will give the values. Because the steam tables will not be provided, right? Because in the same exam hall there will be a number of people writing. I think in the question itself they will give the values. Assume these are the values. Even though I'll ask them for the clarification, and then I will let you know, okay? I'll ask the coordinators of this batch, the NPTEL one, and then I will clarify this question, okay? The questions are, just let me know. I will write down the, okay, so I'll write down the questions. So you asked me for the steam tables. So when is the exam?
18th, sir.
It's April 18th.
Yes.
Okay, I'll let you know by tomorrow. Okay, I'll send the message in the discussion forum.
Okay.
Okay. So it will be Saturday. So you have any doubts in statistical or classical? You can ask. I'll share the notes if you want any notes also by tomorrow. Whatever said in the class, if you want the notes for any specific topic, I can provide it in the drive link. So let me know that if you need any notes.
Sir, is there any previous year questions available?
No, it won't be there with me. Actually, I'm new to this course, right? So I think it won't be available. You can. I'll ask this also. I'll ask the previous year question papers.
Okay, sir.
So after this call, I'll mail them for these things. So the doubts regarding this, then I'll let you know the steam tables. If the questions are given with anything to assume, whether they will give the assuming values or not, and if possible, any previous year question papers.
Okay.
Okay, fine. Is there any other questions?